Welcome to AI Frontiers, where we explore the cutting edge of computational research. Today we're diving into breakthrough research from the field of data structures and algorithms, featuring papers published in the last half of June 2025. These aren't just abstract mathematical exercises. They're the building blocks of our digital world, revealing computational possibilities that could reshape everything from smartphone memory management to global supply chain optimization. Picture this. Every time you ask Siri a question, search for something on Google, or navigate through traffic using your phone, you're witnessing the invisible magic of data structures and algorithms at work. These mathematical marvels are processing billions of operations per second, finding needles in haystacks the size of entire libraries, and solving puzzles that would take humans lifetimes to complete. But here's what might surprise you. Some of the most fundamental problems in computer science are still being cracked open by researchers today, revealing solutions that could revolutionize how we interact with technology tomorrow. Our exploration focuses on the data structures and algorithms field, examining papers published between June 15th and 30th, 2025. This research extends far beyond abstract mathematics to deliver practical impact across our digital landscape. These computational frameworks serve as the building blocks of our digital world, with breakthroughs that could reshape everything from how smartphones manage memory to how supply chains optimize their operations. The 62 papers we've analyzed reveal a field in rapid evolution, responding to the demands of our increasingly complex digital environment. Think of data structures and algorithms as the DNA of computing. Just as biological DNA contains the instructions for building and maintaining life, these computational frameworks contain the instructions for organizing information and solving problems efficiently. Data structures function as the filing systems of the digital world, determining how information is stored, organized, and accessed. Algorithms serve as the step-by-step recipes that tell computers exactly how to manipulate this information to achieve specific goals. The field encompasses everything from basic operations like sorting numbers to incredibly complex challenges like finding shortest paths through networks of millions of interconnected points. What makes this field captivating is its dual nature, simultaneously deeply theoretical, involving complex mathematical proofs, and intensely practical, with direct applications touching every aspect of our digital lives. The first major research theme emerging from recent papers focuses on fault tolerance and robustness. In our interconnected world, systems must continue functioning even when parts fail or come under attack. Think of this like designing a city's infrastructure to keep functioning during natural disasters. The research on ultra-resilient superimposed codes by DeMarco and colleagues exemplifies this perfectly. They've developed coding systems that can handle both timing mismatches and data corruption simultaneously, like creating a communication protocol that works even when messages arrive out of order and some words get garbled in transmission. This advancement addresses the critical need for reliable communication in distributed systems, where perfect synchronization is impossible and communication channels are inherently unreliable. The second prominent theme focuses on dynamic and streaming algorithms. Traditional algorithms were designed for static data that doesn't change during computation, but modern applications deal with information that flows like a river, constantly changing and updating. The work on temporal triangle counting by Venturine and colleagues tackles this challenge head-on, developing ways to analyze relationships in networks where connections appear and disappear over time. This is like tracking friendship patterns on social media as they evolve, requiring algorithms that can process massive streams of relationship data, while maintaining accuracy about temporal patterns. This research enables real-time analysis of dynamic networks, opening new possibilities for understanding everything from social media dynamics to biological networks that change over time. The third theme centers on space-efficient computation and compression. As data volumes explode exponentially, the ability to process information using minimal memory becomes crucial. It's like trying to organize an ever-growing library in a space that isn't getting any bigger. The research on suffix tree compression by Becker and colleagues shows how to dramatically reduce the space needed to store text indexes while maintaining lightning-fast search capabilities. This breakthrough could significantly impact text processing applications, search engines, and bioinformatics tools that need to work with massive textual datasets. The elegance lies in achieving compression ratios proportional to the compressed text size while preserving efficient query performance. Now let's explore the most exciting discoveries emerging from this research. The first major breakthrough comes from coding theory, where DeMarco and colleagues have created the first polynomial time construction of codes that simultaneously handle cyclic shifts and partial corruption. The second groundbreaking result addresses computational statistics, with Hafner and colleagues developing the first algorithm for sampling from time-varying probability distributions with perfect accuracy and constant time complexity. The third significant finding revolutionizes temporal network analysis, with Venturin and colleagues creating streaming algorithms that process massive temporal graphs with billions of edges. The fourth breakthrough tackles text indexing compression, achieving dramatic space reductions while maintaining instant search performance. The fifth major finding provides new insights into network robustness, developing the first logarithmic approximation algorithms for domination problems crucial for maintaining connectivity when nodes fail. For our paper of the day, we focus on the remarkable work by Hafner and colleagues on exact sampling from dynamic discrete distributions. This research addresses what might seem like a narrow technical problem, but actually touches on fundamental questions about maintaining perfect accuracy while adapting to changing conditions in real-time systems. The challenge they tackle is deceptively simple to state, but incredibly difficult to solve. Imagine having a weighted die where the weights on different faces can change over time. You want to roll this die and get results that perfectly match the current weights, with the ability to update weights instantly when they change. The classical solution, called the alias method, works perfectly for static weights but requires complete reconstruction when weights change, making it impractical for dynamic situations. Previous attempts to solve this problem suffered from a fundamental flaw. They used floating-point arithmetic in ways that could accumulate errors over time, leading to biased results. It's like having a scale that gets slightly less accurate with each use, eventually giving completely wrong measurements. For applications like Monte Carlo simulations or machine learning algorithms, this bias can completely invalidate results. The breakthrough insight underlying their solution is that exact sampling can be maintained even with limited precision arithmetic, provided the algorithm is designed carefully to avoid numerical errors. They developed a technique called exact bucket sampling, or EBUS, which maintains a hierarchical structure that organizes probability distributions into buckets at different levels of granularity. The elegance of their approach lies in how it handles updates. When an element is added, removed, or has its weight changed, the algorithm updates only the affected parts of the hierarchy. This allows both sampling and updates to be performed in constant time, regardless of how many elements are in the distribution. The exactness guarantee comes from careful handling of numerical precision, representing probabilities using a specific format with bounded precision and exponent to perform all operations exactly, without accumulating floating-point errors. What makes this work particularly remarkable is that their exact algorithm is not only theoretically superior, but also practically faster than existing approximate methods. This breaks the usual trade-off between accuracy and speed, achieving both objectives simultaneously. In extensive experiments, EBUS consistently outperforms existing methods while providing perfect accuracy guarantees. Looking toward the future, the research themes and methodologies explored today point towards several exciting directions for the field. The integration of machine learning with traditional algorithmic approaches is still in its early stages, with enormous potential for creating adaptive systems that learn from experience while maintaining mathematical guarantees. The development of algorithms for quantum computers represents another frontier that could revolutionize computation, with potential for exponential speedups on certain problems transforming fields from cryptography to optimization. Perhaps most importantly, the field is becoming increasingly interdisciplinary, drawing insights from physics, biology, economics, and other fields to solve computational problems. This cross-pollination is accelerating progress and leading to unexpected connections between seemingly unrelated areas. The challenges of big data and real-time processing continue to drive innovation in streaming algorithms, sketching techniques, and approximate methods. Today's journey through the cutting edge of data structures and algorithms reveals a field that's both building on decades of foundational work and boldly exploring new frontiers. From ultra-resilient coding systems that handle chaos and corruption to exact sampling algorithms achieving perfect accuracy in dynamic environments, these advances are reshaping our understanding of what's computationally possible. The common thread running through all this research is the recognition that the challenges of our digital age require new approaches that combine mathematical rigor with practical effectiveness. The researchers whose work we've explored today are not just solving abstract puzzles, they're creating the computational tools that will power the next generation of technological innovation. This episode demonstrates how AI synthesis, using Claude's Sonnet 4 model, TTS synthesis, powered by Deepgram technology, and image generation utilizing OpenAI capabilities, can collaborate to create comprehensive research summaries. Human expert review of synthesized content ensures accuracy, though potential oversights may exist. This process represents the cutting edge of AI-assisted research communication, making complex computational advances accessible to broader audiences while maintaining technical accuracy and depth. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from Archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archivepreprinserver.org, content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archivepreprinserver.org.